Okay, hi. Let's go ahead now and finish up as much as we can the 2 by 2 systems. This time, let's look at complex eigenvalues. And as usual, I'll be writing on a whiteboard using this little dumb little web tablet. I think it'll work okay. And let's start the screen. And let's suppose we start with our matrix now. Again, once again, we have x prime equals ax is our differential equation. And here, let our a look like this. Minus 10. Oh, I didn't want that. Let's just get rid of that. I want minus 1, 10, minus 10, and negative 1. Now, if I try to calculate a minus lambda I, as usual, we have a minus 1 minus lambda, 10 minus 10 minus 1 minus lambda. Notice that's the same. Then if you take the determinant to get the characteristic equation, notice this is 1 plus lambda, the negative of that squared. So what you really get, because you're squaring this, minus 10 plus a minus 10, it's a minus 10, but you're adding it, so that's 100. So the solutions here, to make that a 0, you're going to need complex numbers. So your lambda will be a minus 1 plus 10i, plus or minus complex conjugates. So running with the lambda equals a minus 1 plus 10i, a minus lambda I. Well, the ones just cancel, and I have a minus 10i, 10 minus 10, and I have a minus 10i. And an eigenvector there, we can do it by inspection. If we have a 1 up here, and we have an I downstairs, that works, right? So minus 10i plus 10i is correct. Or minus 10 plus minus 10 times minus 1, that works. So in fact, we have our complex eigenvector here. All right, so we're good. So now let's go ahead and try to, we got our complex eigenvector and our eigenvalue. So therefore, our solution looks like this. It looks like e to the minus 1 plus, I'm going to use the plus, times this particular eigenvector. And I'm going to rewrite this as e to the minus t. And then keep in mind that e to the 10i is going to be cosine 10t plus I sine 10t times 1i. I better close this up. Now what I'm going to do is I'm going to do this multiplication. I'm going to keep the e to the minus t outside. Then if you multiply the x coordinate, you get a cosine of 10t. Then I'm going to go ahead and write this as real and imaginary parts. And I have a sine of 10t. And if I'm doing it this way, I better multiply the c to the minus t by the whole thing. Now notice when I multiply this I right here, I get a cosine of 10t here. Because this, and the I times I gives you a minus sine of 10t. So this kind of looks like it might be a little bit more complicated, but it's not really, because remember, our two solutions will come from the real part and the complex part. So the real part will have e, let's see here, e to the minus t. Well, come to think of it, I better write it like this. So now our two solutions are the real part and the complex part. So we get that. Now, suppose we'd like to solve for x of 0 equals 1 and y of 0. That's a nice easy one. And keeping in mind that we're looking at the real parts and the complex parts. And e to the 0 is just a 1. Well, your x will be e to the minus t cosine 10t plus taking the complex part and your y will be minus sine 10t plus cosine of 10t. So that's going to be our solution here. Now, let's take a look at what that looks like graphed. And if we go to parametric, I've already entered this. And take a look at what you have. Now, as t goes to infinity, we're now going to 0. So this is what's known as a sink because the arrows are going in like this, right? So you start here and you endlessly spiral in. And you can see this. I'll just expand the equation a little bit so you can see this a little better. These are the equations already inputted. And you can see how the spiral goes like this. Spiraling in, death spiral, if you will. Now, if you go to the phase plane, I've already plotted the equation in the phase plane, and just taking a random one, you can see how the arrows are indicating the direction that you go along these lines. So if you do another one, you get another spiral. So all of the trajectories are spirals that spiral in like this. So this is a classic, what we call a, well, let's see, I better pick this air here. Make it even bigger. Then go back up. This is what we call a spiral sink. It becomes a source if the coefficient of t is positive or the real part is positive. Now let's look at something called a center. And the center has pure imaginary eigenvalues. And the simplest one, I think, would be the 0, minus 1, 1, 0. That would be something that has that. Starting with this, if this is our A minus lambda I is minus lambda minus 1, 1 minus lambda. And the determinant is going to be lambda squared plus 1. So lambda is equal to plus or minus I. So use a lambda equal plus I. What I get is a minus I, negative 1, 1 minus I. And an eigenvector here would be, I would think, would be 1. And let's see, if I put an I here, that'd be a negative I, so I better put a negative I like so. Negative I times the negative 1 is a positive I, and that works, right? So our solution is going to be e to the it. Breaking this down into real and imaginary parts, that's cosine of t plus I sine t times 1 negative I. And that, of course, gives us x using is going to be cosine t plus I sine t. Or y would be, now multiplying by negative I here now, would be negative I times times I is a positive 1. So I want to make sure that's right. Yeah, that's positive I. Yeah. So that's, and so now we take real. Kind of screwed that up. That was stream of consciousness. Real imaginary parts. So we can now try to plot this up, and let's just do this right here. This is, go back. This is cosine sine, sine minus cosine. Cosine. All right, let's make sure here. It's cosine of t plus sine of t, because we're taking the real and imaginary parts. And then the last part is going to be sine minus cosine. And lo and behold, you get a nice little circle like is expected. You can work this out and see why, with some trig identities. Now, the face plane is kind of interesting as well. Let's go ahead and do this. And again, this is kind of, you have to be careful here. The A I used to get the center, and that's what this is called. It's called the center. It's 0, negative 1, 1, 0. Negative y, x. And we graph the phase plane, and we just draw normal things, and you get closed. This is the center. Now, not every center is a perfect circle. You could, change it just a little bit. Let's say you had 2 times x. And here you get ellipses. So you can, it's not all centers are perfect circles, but they are closed. And they can be slanted, right? So just showing you the sorts of things that can happen here. So we've done the real eigenvalues, real distinct, with the same sign in different signs. And then we did the spiral, and I showed you a spiral sink. Now, if you change the real part of the eigenvector to positive, it's a spiral source. So that's this part right here, and thanks for watching.